Okay, let's try to calculate magnetic field. Let's try to calculate magnetic field for infinitely long straight conductor with electric current. For infinitely long straight conductor. So I will make a picture. I'll make a picture for this. I'll make a picture. It can be shown. It can be shown in this way. This picture, and we have electric current here. Electric current I, and it is necessary. It is necessary to calculate absolute value of magnetic induction. Absolute value of magnetic induction. And the first question is how to draw line of magnetic field. Which form lines of magnetic field will have? Which form? How do you think? It will have the same symmetry as symmetry of system that produced magnetic field, because every field, all fields, magnetic, electric fields, always have the same symmetry as system that produced these fields. So according to this, we can conclude that lines of magnetic field will have form of circles. I'll show them with red line, and what is necessary to say that a part of this line that is behind the screen, I will show with dash line. Dash line is a part of this line of magnetic field that is behind the screen. Okay, this is a line of magnetic field, but the direction of this line, there may be two situations. It may be this direction, or it may be this direction. And the question is how to define the correct direction of line of magnetic field. How to define the correct direction. Okay, we can define this. With right hand rule. So how to use this? Let's imagine that thumb of right hand shows the direction of electric current. If thumb of right hand shows the direction of electric current, other fingers other fingers will show the direction of magnetic field. So if here is electric current, so here we'll have the direction of magnetic field. So according to this, we have to choose this direction. This direction will be correct. This direction will be correct in this situation. Okay, do you have any questions about this? No questions. No questions. And okay, let's. I will draw a radius of this circle. I'll sign this radius with letter D. Radius of this circle is D. Circle is a line of magnetic field. It is circle because in this case it has the same symmetry as a long straight conductor or long straight current and let's try to define magnetic field, absolute value of magnetic field on distance d from the straight conductor. Do you have any ideas how to calculate this magnetic field in this situation? Do you have any ideas how to do this? No ideas. Okay, it is possible. It is possible to use Biot-Savart law. It will work in this situation, but it is more difficult. It is more difficult to use this law in this case. I think the better way in this situation is to use Ampere's circuital law. Ampere's circuital law is better for this exercise. So let's try to remember this Ampere's circuital law. In the left side of the equation we have linear integral b dl and this is equal okay, and what will be in the right side? Can you remember? What will be in the right side of this equation? No ideas, but we have spoken about this on previous lessons. In the left side will be mu zero sum of electric currents that passes through the circuit. So it will be sum of electric currents. And to use this, the first step is to choose. The first step is to choose the best circuit. The best circuit that will allow us to calculate this integral, without knowledge about function b, about vector b, because we still don't know the absolute value of this vector. We still don't know this. So it is necessary. To think up something. To make the situation simpler. Okay, and to do this, it is necessary to choose the best circuit. And there are only two type exercises for Ampere's circuital law, and this is one of them. For first type, the best circuit will be a circle. This is first type, and for second type of exercises, the best choice will be rectangle. So in this case, the best choice is a circle. And what circle will we choose? We will choose the same circle as a line of magnetic field. So this will be circuit L. And the direction of the element of this circuit dl will have the same direction as vector b. So I'll try to show this on picture. So here we have the element dl. So the element dl has the same direction as vector b, according to our choice. Okay, and in this situation, we can simplify linear integral. We may simplify linear integral b dl is equal. This is equal to b. This is equal to b dl but I have forgotten to say something about the direction of vector b and vector dl, about their directions. Directions of vector b and dl will be the same. They have the same direction, so we can sign this with two parallel arrows. So these two parallel arrows mean that vectors b and dl have the same directions. And here, according to the definition of scalar product of vectors, we have absolute value of b, absolute value of dl, or modulus So cosine. Here we have cosine, and and uh, uh, and what angle? What angle will be between vectors b and dl? What angle should we write here? How do you think? 45 degrees, you think? Okay, let's try to let's try to understand this 45 degrees. 45 degrees is we have when vector b, for example, is for vector b. This is vector b. This is vector b, and if we have dl vector here, if we have dl here, dl dl. So in this situation, we have angle. We have angle 45 degrees. 45 degrees in this situation. In this situation, but we don't have this situation. We don't have this situation because we have this. Because we have this. So it is necessary. It is necessary some another idea. It is necessary to think up something else. When two vectors have the same directions. Because in these situations, directions are not the same. In this situation, directions are not the same. So what will be in case when they have the same direction? What angle? Okay, do you have any more ideas? Okay, this, if we show this on picture, this means that, for example, vector b is here. For example, vector b is here, and for example, vector dl is here. This is vector dl. Okay, and so what angle should we write in this situation? According to the picture. Okay, 0 degrees. Yes, it will be 0. It will be 0. I agree, it will be 0. I agree that it will be 0. And so we can write that it will be 0 degrees. It will be 0. It will be 0. So it means that if we have 0, because we have chosen such circuit L, that angle between vectors B and DL is equal to 0. Okay, but if we have cosine 0, what will we have here? So how to calculate cosine of 0 degrees? Yes, it will be 1. So we have B and DL. We have B and DL. Okay, we have B and DL. B and DL, I agree. B and DL. So we have here and here we have the same situation, but this this uh, this expression doesn't have any vectors. And uh, this is good news for us, because numbers are usually simpler to treat with than vectors. So according to this, we can write that this integral will become more simpler. This integral becomes more simpler uh, because now it doesn't contain vectors. Now it doesn't contain vectors because of this. Now it doesn't contain vectors. It contains only moduluses of vectors. Okay, and moreover, uh, if closed circuit is the same as line of magnetic field, and according to the symmetry, according to the symmetry, according to the symmetry, uh, according to the symmetry, the absolute value of vector B will be the same for all elements DL. So B doesn't depend on DL, and the B may be written outside of the integral. So here we have DL. It may be written outside of the integral. Okay, and how do you think how to calculate this integral? If we add all elements, of circle, I will write. I will write this. I will write this. I will write this. I'll write this circle, and let's imagine that we want to calculate uh, radius is equal to d. Radius is d, and the element of this circle is dl. The element of this circle is dl. Here we have dl. dl. Okay, and according to the definition of the integral, uh, so this is circuit L. This is circuit L. So according to the definition, according to the definition, here we have dl, and this will be just sum of all elements dl. So it will be just sum of all elements dl. Okay, and if we add all elements dli, if we add all the elements, what will we get as a result? What will we get as a result if we add all parts of the circle? What will we get if we add all parts of the circle? I think we will get the whole circuit. So we will get the length of the whole circuit. We will get length of the whole circuit in this situation. We will get length of the whole circuit, and so we will have the length of the circuit. And can you remember length of the circuit? Length of the circle. I mean, it will be double P and multiplied by D. D in this case, D is a radius of the circle. This is radius. So double P multiplied by radius is equal to the length of the circle. Okay, and so it means that this integral will be equal to 2pd. Double P multiplied by D. Double P multiplied by D. Double P multiplied by D. Okay, do you have any questions about this? No questions. No questions. No questions. If there are no questions, let's continue. Let's continue. So we have managed to calculate the integral in the left side of Ampere's circuital law. We have managed to calculate the left side of the Ampere's circuital law. Okay, and what about right side? What about right side? This is the sum of electric currents that passes through circuit L. Sum of currents that pass through circuit L. What will we have? What will we have here? How do you think? According to the picture. Okay, any ideas? But we have just one electric current. We have just one electric current. There are no other currents. There are no other currents. So we can. It is easy to define that if we have only one electric current, the sum of currents will be equal to this current, and this current passes through the chosen circuit. Okay, and the next step is to substitute obtained results into Ampere's circuital law. The next step is to make substitution, and so we will have B multiplied by 2 P D multiplied by 2 P D, and this will be mu 0. This will be mu 0 and I electric current. Here we have electric current. Here we have electric current. Here we have electric current. Okay, and what will we have? What will we have next? Next, we will get that absolute value of vector B is equal to mu 0 I divided by 2 P and D. 2P and D. Do you have any questions about this? Now, this is the answer for the first exercise. This is the answer for the first exercise. Okay, let's try to do. I will write this result in a frame. Because this result we can use in future. We can use in future to do the other exercises. So here, if we have such conductor, so we can write that this is magnetic induction, magnetic induction of a straight infinitely long current. Infinitely long. No, maybe it is better to write infinitely long conductor with current. Conductor with current. With current in it. Conductor with current. And this result we may use in future. This result we may use in future. So I will frame this with blue line. The blue line. Okay, do you have any questions about this? Do you have any questions? No questions. No questions. Okay, if there are no questions, let's try to do the same thing for another system. Uh, so magnetic induction. Magnetic induction. Magnetic induction. Magnetic induction of straight induction inside an ideal straight inductor or solenoid. Magnetic induction inside an ideal straight inductor or solenoid. As I can remember, we have used this result yesterday. We have used this result, but without proving this. And now we are going to prove this result. So if we have a straight inductor, it looks like a spring. It looks like a spring. It looks like a spring. And if this inductor is ideal, if it is ideal, so we have external magnetic field that is equal to 0. Magnetic field outside of the inductor, but inside of the inductor, magnetic field will be homogeneous. And the question is how to define modulus of this vector. How to define modulus of this vector. The question is how to define modulus of this vector. Okay, and we know electric current. We know electric current in the inductor. We know magnetic permeability inside inductor, and we know n. We know number of coils. We know number of coils per unit of length. We know number of coils per unit of length of the inductor. So, what ideas do you have? How to calculate this B magnetic field inside the inductor? Oh dear. Okay, I think it is the best way is to use uh, the best way is to use Ampere's circuital law. Ampere's circuital law again. Is to use Ampere's circuital law again. So here we have L, B, B, D, L, B and D, L, and here will be mu zero, and sum of electric currents. Sum of electric currents that pass through the closed circuit L. Okay, and the first step of using Ampere's circuital law is to choose the best closed circuit L. And do you have any ideas what type of circuit should we choose? What type of circuit should we choose? Because before we have spoken that there are two types of exercises. First type was before, and now it is the second type. Now it is the second type of exercises that can be solved with Ampere's circuital law. With Ampere's circuital law. Okay, so how to use this? How to use this in this situation? The best choice of closed circuit will be rectangle. It will be rectangle because I have said before that there are two types of exercises that can be solved with Ampere's circuital law. In the first type, the best choice of circuit will be circle, and the second type, the best choice will be rectangle. So let's choose rectangle as a circuit in this situation. So here we have rectangle, and the direction of this circuit is shown with green arrows. Is shown with green arrows. So these green arrows are elements dl. So this is element dl, this is element dl, and etc. Okay, and here we have distance. For example, here we have distance. For example, L. And how to calculate this integral? I think it is the best way to write numbers of corners of this rectangle. 1, 2, 3, 4. 1, 2, 3, 4, and then we will divide the line integral into 4 integrals. We will divide this into 4 integrals. So first will be b and dl, and we will have 3 similar integrals. So it was second, third, the third, and the fourth integral. And the fourth integral will be here. This is the fourth integral. And so if we have this situation, the first will be for side 1, 2, 1 from 1 to 2, 2, 3, 3, 4, and 4, 1. 4, 1, because we have 4 sides of the rectangle. 4 sides of the rectangle. First will be 1, 2. The second will be 2, 3. The third will be 3, 4, and 4, 1. So we have 4 sides of the rectangle. 4 sides of the rectangle. 4 sides of the rectangle. Okay, and okay, and for example, what can we say? About sides 2, 3, and 4, 1? What can we say about sides 2, 3, and 4, 1? In this situation, for the field inside the inductor, we will have this situation. It is for this part, and for this part. For sides 2, 3, and 4, 1, we will have this situation. And so, according to this, in this situation, B dl vector will be B dl cosine 90 degrees. Okay, and what will be this equal to? How do you think? what will be here? No, here will not be BDL. It will not be BDL because we have here we have cosine of 90 degrees. Cosine of 90 degrees. So it is necessary to remember or find somewhere in reference books or in the internet. It is or to calculate with computer or calculator cosine of 90 degrees. Yes, it will be 0. It will be 0. Okay. Okay, I agree. It will be 0. It will be 0. So it will be 0. And this result is true for this integral will be 0. And this integral will be 0. And this integral will also be 0. Okay. Okay, and what about the side? What about this side? What about this side? In this situation, according to the condition, we have that external magnetic field is almost equal to 0. This is almost equal to 0. So it means that this third integral is equal to 0 either. This is equal to 0. Okay, and the last integral, it is better to rewrite this. So we have obtained only one integral because these three integrals are equal to 0. They are equal to 0. So we have obtained only one integral. And here we can see for this integral we can see that for side 1 2 we can see that vector b in this situation, vector b has the same direction as vector dl. Okay, and it means that b dl is equal to b dl cosine. And what angle will be here? How do you think? But why 90 degrees? Why 90 degrees? Look at picture. Look at picture. What will be the angle between green arrow and red arrow? Oh, okay. It will be 0. It will be 0. So it will be 0 for. It will be 0 because we have the same direction. We have the same directions for vectors b and dl. So here it will be 0, and what will we have as a result? Okay, B dl. Yes, in this situation we will definitely have B dl. We will definitely have B dl. Okay, great. It will be B dl. B and dl. Yes, and I can write that it will be B dl. So it will be integral on side 1, 2, B dl. B dl without vectors. And the magnetic field inside the inductor is homogeneous. Magnetic field is homogeneous. It means that it doesn't depend on dl and may be written outside of the integral. dl. And this sum of all elements dl will be equal to this distance. It will be equal to this distance. So it will be B. It will be B multiplied by L. It is equal to B multiplied by L. Okay, do you have any questions? No questions. No questions. Okay, so I will remove some things that we don't need anymore. I will remove them, and we have obtained that this integral for this case, for this exercise, is equal to B multiplied by L. Okay, and what about sum of electric currents that passes through this circuit? This green rectangle is circuit L. So this question, sum of these currents, this question is more difficult than it was before, because we have many coils. We have many coils, and it will be number of coils per distance L, number of coils multiplied by electric current. And this number of coils is equal to number of coils per unit of length multiplied by L, and electric current will be still here. Okay, so we have calculated left and right sides of Ampere's circuital law, and because of this, we can say that it will be B L is equal to this is equal to mu 0 n L I. And from here we have that magnetic field inside the inductor. Inside the inductor will be mu 0 n I. It will be mu 0 n I. Okay, do you have any questions about this No questions. No questions. Okay, if there are no questions, if there are no questions, uh, if there are no questions, I'll remove some things that we don't need anymore from the screen. That we don't need anymore, and we can say that yeah, we don't need this 1 and 2. So in this case, we have this formula. Okay, do you have any questions about this? No questions. No questions. No questions. And it is necessary to think that the next homework will be exercises from electricity and magnetism. And here exercise number 14 and number 15. 14 and 15. It will be the next homework. Okay, do you have any questions? No. And if there are no questions, thank you for your attention. Thank you for your attention, and I hope to meet you next week. Thank you for your attention, and I hope to meet you next week.